This PowerPoint presentation deals with Chapter 4 of the AMS Weather Studies, Introduction to Atmospheric Science, for MVCC's WE 101 course. The topic of this particular PowerPoint is heat, temperature, and atmospheric circulation. One of the questions that we can ask ourselves is, what is temperature? What is heat? How are they different? And what effect do they play on the Earth atmosphere system, especially in terms of weather? This particular chapter will cover the ability to distinguish between temperature and heat, the heat transfer process, and thermal responses, as well as specific heat imbalances, and how does heat affect atmospheric circulation. If we were to describe weather, we could really say it fairly simply. Weather is the unequal heating of the Earth, and that's really what weather is all about. So this particular chapter is very, very important for us to appreciate. From everyday experience, we know that air temperature varies with time from season to season, and actually between day and night, and even from hour to hour in some cases. Air temperature also varies from place to place, and one of the more extreme areas for weather is Death Valley, California. Now, your particular PowerPoint slide here says that it's the second highest temperature ever recorded on Earth in 1913 at 134 degrees, but actually with recent analysis it's found to be actually the highest temperature ever recorded, because the other temperatures that were higher were proven to be false. This slide distinguishes the difference between temperature and heat. When we talk about temperature, the temperature really is nothing more than the kinetic energy of atoms or molecules that are moving very rapidly in a particular substance. This particular temperature varies with the increase of kinetic energy. The higher the molecules or faster the molecules move, the greater the temperature. If two objects have different temperatures, that is, different average kinetic molecular energies, and these are brought together into contact, molecular collisions will transfer energy between these two objects, and we call this energy in transit heat. Heat transferred from one object reduces the internal energy of that object, whereas heat absorbed by an object increases the internal energy. So heat and temperature are really related, but two different things. To measure temperatures, we use a variety of different temperature scales. We can see three of the more common ones here: the Kelvin, the Celsius, and the Fahrenheit scale. Each of these is used in meteorology, with the temperature and the Celsius and Fahrenheit being the more common of the two. This figure in your text gives you a relative relationship of the three different scales, with the table actually showing you how to convert from one to another. Although temperature is a convenient way to describe the degree of hotness or coldness of an object, we can also quantify heat energy directly. Recently, or up until recently, common measures of heat energy were units called calories, and it's defined as the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. This particular word calorie can be confusing, because we also use calorie as the measure of energy content of the food, and actually that calorie is a kilocalorie, kilo meaning 1,000, and that's really a big C versus the little c that we use relative to this temperature we are concerned with. We now use a more common term called the joule, and 1 calorie equals 4.18, etc., joules. The English quantify heat in the terms of British thermal units, or BTUs, and that is shown here as 1 BTU is equal to 252 calories, or 1055 joules, and this is the energy required to raise not 1 gram of water, but 1 pound of water 1 degree Fahrenheit, not 1 degree Celsius. So this can be confusing, but each of these has a unique place in understanding the relationship between temperature and heat. You all appreciate the fact that to measure temperature we use things called thermometers. And interestingly enough, Galilei is credited with the first thermometer back in 1592 or so. One of the more common types of thermometers that you're familiar with is the liquid in glass thermometer. This is a very common type of thermometer that has a graduated scale on it and uses alcohol or mercury as the liquid in the thermometer. What happens is when temperature changes, the glass and the liquid expand when heated and contract when cooled, but the liquid does so much more than the glass. So the heat transferred basically brings about the expansion of the liquid and the glass, but liquid much more, so the liquid tends to rise or fall depending on the particular temperature. This particular thermometer is called a bimetallic thermometer, and this thermometer has some bimetallic sensing elements to take advantage of the expansion and contraction that accompanies the heating and cooling of metals. With that, we then see that the temperature will change relative to the pointer, which is connected to the bimetallic elements. For the radiosondes which are sent up into the atmosphere, they have what is known as an electronic thermometer, and they send information back to the station, and this particular thing called a thermograph is what is formed with the information that is sent back from these balloons in the higher atmosphere. And we can see changes in the temperature with cold fronts, warm fronts, etc. So that's found in these high balloons that we use to measure the atmospheric temperature. For in situ measurements of air temperature, which represent the local atmospheric environment, ideally the thermometer should be adequately ventilated in thermal equilibrium with its surroundings and shielded from precipitation. This particular National Weather Service electronic temperature sensor gives us an idea as to how they shield the sensors from direct sunshine, precipitation, etc. A change in temperature with distance is known as a temperature gradient. We know that heat flows in response to a temperature gradient, and according to the second law of thermodynamics, when a temperature gradient exists, heat is transferred in a direction so as to eliminate that particular gradient. Heat flows from where the temperature is higher toward where the temperature is lower. In addition, the greater the temperature difference, that is, the steeper the temperature gradient, the more rapid the rate of heat transfer. Think of yourself riding around in an air-conditioned car. You open the windows, and in a very short period of time, the gradient has disappeared, where the cold and the warm now mix to form this new temperature. Within the Earth-atmosphere system, heat is transferred in a number of ways, as listed here, by radiation, conduction, convection, and by something known as latent heat, or the heat that's released or consumed by phase changes in water. Liquid to ice, ice to liquid, liquid to vapor, etc. As we know from the last chapter, radiation describes both a form of energy and a means of energy transfer. We've talked about electromagnetic radiation, and we know that it can travel through a vacuum. We also know that radiation is the principal means whereby the Earth atmosphere system gains energy from the sun. We also remember from Chapter 3 that radiation is also the principal means whereby heat escapes from the planet to space, thus maintaining a habitable environment on the surface of the Earth. The absorption of radiation, that is the conversion of electromagnetic energy to heat, causes temperatures of objects to rise. And we talk about radiational heating and also radiational cooling. If an object emits radiation at a greater rate than it absorbs, the temperature of the object will obviously fall, and that's what radiation cooling is. Another heat transfer process is called conduction, which basically refers to the transfer of kinetic energy between neighboring molecules. As we can appreciate, some substances are better conductors of heat than others. Heat conductivity is defined as the ratio of the rate of heat transfer across an area to the temperature gradient. As a rule, solids are better conductors of heat than our liquids, and liquids are better heat conductors than gases. At one extreme, metals are excellent conductors of heat, whereas at the other extreme, still air is a very poor conductor of heat. The table listed 4.2 gives us some common substances and are listed as the most to least conductive. So copper is a very good conductor. Water and air, as you can see, are not nearly as good as some of the solids listed above them. Another heat transfer process is a process called convection. And this is the transport of heat within a fluid being basically a liquid or gas, by way of motions of the fluid itself. Although conduction takes place in solids, liquids, and gases, convection generally occurs only in liquids and gases. This is a very important process for transferring heat in the atmosphere, and convection in the atmosphere is a consequence of differences in air density. At the same pressure, cold air is denser than warm air. As heat is conducted from the relatively warm ground to, say, cooler overlying air, that air is heated, becoming less dense and thus more buoyant compared to the surrounding air. This process of transferring heat in the atmosphere brings about something called a convection cycle. Ascending warm air expands, it then cools and eventually sinks back to the ground, as demonstrated by the graphic in this particular PowerPoint. The combination of conduction and convection is known as sensible heating, and that's because we can sense a change in the temperature in response to these heatings. So sensible heating is a term we'll be using from time to time, and that relates to both conduction and convection, or the combination of. The last of the heat transfer processes we're going to discuss in this PowerPoint is called latent heating. The quantity of heat that's involved in phase changes of water, that is liquid to solid, etc., is known as latent heat, where the term latent actually refers to the meaning hidden, until of course it's released. Heat is absorbed or released during phase changes because of differences in molecular activity, represented by the three phases of water: solid, ice, liquid, water, or vapor. All of these phase changes deal with what we call latent heat. This diagram shows you what happens in terms of latent heat being absorbed or released to the environment based on the phase change that it's going through at this particular point in time. This is a very, very important process in the atmosphere in terms of heat transfer. Whether by radiation, conduction, convection, or latent heat, the transfer of heat from one place to another within the Earth atmosphere system is accompanied always by changes in temperature. Heat gain causes rise, and heat loss causes cooling in terms of air temperature. The temperature change accompanying an input or output of a specific quantity of heat varies from one substance to another. Table 4.3 shows us that, and the amount of heat that will raise the temperature 1 gram of a substance by 1 degree Celsius is defined as specific heat of that particular substance. Notice that water has a relatively high specific heat. In fact, the specific heat of all substances is really measured relative to that of liquid water, that is 1 calorie per gram per Celsius degree. The contrast in specific heat is one reason why the sand is hotter than water. For instance, sand heats up a lot more quickly than water does. It takes a lot more energy to get water and its molecules moving, that is increasing the temperature, than it does for sand on a beach. So sand becomes relatively hot, whereas water will remain relatively cooler. So water has this exceptional capacity to store heat, and this ability has some very important implications for weather and climate, especially in the middle and higher latitudes. You can appreciate that a large body of water in a particular area can significantly influence the climate in and around that particular area because it acts as a thermal component. In other words, a large body of water exhibits a greater resistance to temperature change, and we call that the thermal inertia. This particular graph shows us how water has an effect on climate. This being St. Louis, which is not near a body of water, versus San Francisco, which is near a relatively large body of water called the Pacific Ocean. And we see that the maritime climate is very different than the continental climate in terms of maintaining a relatively consistent temperature throughout the year. This is due to the thermal inertia of this large body of water resisting temperature change in this environment. Weather, we know, is a response to unequal rates of radiational heating and radiational cooling within the Earth atmosphere system. These imbalances are responsible for temperature gradients within the Earth atmosphere system, in response to which the atmosphere circulates and redistributes heat. In terms of us understanding this, we have taken monitoring the atmosphere through satellites and have come up with some very interesting data relative to the heat imbalance within the Earth and the atmosphere. This data has shown us that Earth's surface has a net radiational heating, while the atmosphere has a net radiational cooling. So Earth's surface transfers heat to the atmosphere to try to maintain a balance and make up the difference between the two. This particular diagram shows basically the solar radiation fluxes that are depicted, and they're on the left. The infrared radiation fluxes are in the middle, and the latent and sensible heat fluxes are on the right. Now, what this basically tells us, if we look at the next slide, that there is a global radiation balance of net cooling, net heating, and transfer as far as we're concerned relative to the Earth atmosphere system. As Earth's surface absorbs radiation, both solar and infrared, some of the heat energy is used to vaporize water from oceans and lakes, rivers, and vegetation, a process called transpiration, without changing temperatures. The latent heat required for vaporization, that is evaporation or sublimation, is supplied at the Earth's surface, and heat is subsequently released to the atmosphere during cloud development. Within the troposphere, clouds form as some of the water vapor condenses into liquid water droplets or deposits as ice crystals, depending on how high the water is in the atmosphere. During cloud formation, water changes phases and latent heat is released to the atmosphere. Through latent heating, the heat is transferred from the Earth's surface to the troposphere. In fact, latent heat transfer is more important than either radiational cooling or sensible heat transfer in the cooling of the Earth's surface, and that's very critical to appreciate. This diagram gives you some indication as to the energy related to temperature in terms of changing water through its different phases. Heat transfer via conduction and convection can be monitored, that is, we can sense it, by temperature changes, and we can measure it by way of thermometers. Hence, sensible heating encompasses both of these processes. Heat is conducted from the relatively warm surface of the Earth to the cooler overlying air. Heating reduces the density of that air, which is forced to rise by cooler, denser air replacing it at the surface. In this way, convection transports heat from the Earth's surface to the troposphere. Because air is a relatively poor conductor of heat, as we saw earlier, convection is much more important than conduction as a heat transfer mechanism within the troposphere. In terms of heat imbalance, the Bowen ratio is very important to appreciate. This is named after an astrophysicist whose name was Ira Bowen, worked at California Institute of Technology. And this ratio describes how the heat energy received by the Earth's surface by way of absorption of solar and infrared radiation, how this heat is partitioned between sensible heating and latent heating. Keep in mind the difference between sensible and latent heating. As you can see from the table, the average Bowen ratio varies from one place to another depending on the amount of surface moisture. The wetter the surface, the less important is sensible heating, and the more important is latent heating, that is, changing phases. The Bowen ratio ranges from about 0.1, that is 1/10 as much sensible as latent heating for the oceans, to about 5, that is 5 times as much sensible as latent heating in things called deserts. Ocean waters cover much of the Earth's surface, so it's not that surprising that the global Bowen ratio is relatively low. This particular diagram shows us the effects in a desert locality that sensible heating exceeds latent heating. Sensible heating, latent heating. Notice in Wisconsin, a much more humid environment, that latent heating is greater than sensible heating for much of the year, from April to November, and the Bowen ratio reaches a maximum of in June or July. This next slide shows us some variation by latitude of absorbed solar radiation and the outgoing infrared radiation based on measurements flown onboard Earth orbiting satellites. And this indicates that the division between regions of net radiational cooling and regions of net radiational warming is close to the 35-degree latitude circle in both hemispheres. If true, latitudes poleward of about 35 degrees should experience a net cooling over the course of the year, while the tropics should increase significant warming. In fact, lower latitudes do not become progressively warmer, nor do higher latitudes become progressively cooler. And that's because heat is transported poleward from the tropics into the middle and high latitudes. How is this heat transported towards the poles? Well, it's brought about by 1. Air mass exchange, 2. Storm systems, and 3. Ocean currents. With research showing that atmospheric processes account for the vast majority of heat transport both in the northern hemisphere and in the southern hemisphere. This composite infrared satellite image showing these color-coded surfaces with red areas being warm and blue areas being colder. Here's the eastern coast of the United States. We see the Gulf Stream is clearly discernible as a ribbon of relatively warm water flowing towards the pole, and is one of the ways in which transport of heat takes place. So why weather? Well, as we've seen, imbalances in the rates of radiational heating and radiational cooling give rise to temperature gradients between the Earth's surface and the troposphere and low and high latitudes. In response, heat is transported within the Earth atmosphere system by conduction, convection, cloud development, air mass exchange, and various storms. That is, the atmosphere circulates, bringing about changes in the state of the atmosphere, which we call weather. A cause and effect chain that operates in the Earth's atmosphere system, starting with the sun as the prime energy source and unequal cooling of the Earth, is why weather occurs. We know that air temperature is variable, fluctuating hour to hour, day to day, and season to season. Hopefully our discussion of heat transfer processes on the last few slides and the poleward heat transfer provides some insight as to why air temperature is so variable. The number of factors that govern local radiation budget and air temperature include latitude, time and day of the year, solar altitude, cloud cover, surface characteristics, albedo, and a variety of other things. The annual temperature cycle, also called the March of mean monthly temperature, reflects the variation in incoming solar radiation over the course of the year. At the middle and high latitudes, the march of mean monthly temperature lags behind the monthly variation in solar radiation, So the warmest and coldest months of the year typically do not coincide with the times of minimum and maximum solar radiation. As we can see from this particular graph, at relatively high latitudes, the seasonal difference in solar radiation is relatively extreme, varying from near zero in the fall and winter to a maximum of spring and summer. In this particular representation of Kansas City, mid-latitude, we find that the highest extreme for temperature is not at the point where the solar energy is the greatest, which is around June 21st. So the maximum solar input is in this area, but the highest temperature is about 27 or 28 days later here. Over the course of a 24-hour day, surface air temperatures respond to regular variations in the flux of radiation. With clear skies and light winds or calm air, the day's lowest minimum temperature typically occurs shortly after sunrise, after solar radiation equals outgoing Earth radiation. The day's maximum temperature is usually recorded early or mid-afternoon, again when outgoing Earth radiation equals incoming radiation, even though solar radiation peaks around local solar noon. As you can appreciate, surface cover can also have an effect on the variation of air temperatures. Dry soils help explain why unusually high air temperatures are accompanied by drought, a lengthy period of moist deficit. Soils dry out, crops wither and die, and lakes and other reservoirs sink. Because less surface moisture is available for vaporization, more of the available heat is channeled into raising the surface temperature rather than vaporizing the fluids, which in turn raises the temperature through conduction and convection. Snow has a relatively high albedo and substantially reduces the amount of solar radiation that is absorbed at the surface and converted to heat. Snow-covered ground reduces sensible heating of the overlying air because some of the available heat is used to vaporize or melt snow. Air mass advection also is responsible for variation in air temperatures across the specific area. Air mass advection refers to the movement of an air mass from one locality to another, from this direction or this direction, across isotherms. An isotherm is a line drawn on a map through localities having the same air temperature. There is both cold air and warm air advection taking place, where we're moving from colder to warmer areas or warmer to colder areas, and this air advection plays a significant role in the change of air temperature. Additional variations of air temperature can be basically associated with the urban heat island effect as described here. Anytime there is urbanization, there is always a change in land cover and energy use, and this can alter the local radiation budget and therefore the local climate. An urban heat island is identified by a pattern of closed isotherms, that is equal temperatures, encircling a metropolitan area that is significantly warmer than the surrounding rural area. That is an island of warmth surrounded by cooler surrounded air outside of that warm region. This figure shows some satellite maps of Providence, Rhode Island, and Buffalo. Interestingly enough, both cities are about the same size, but Providence is considerably more compact and is surrounded by dense forested areas compared with a higher percentage of farmland which surrounds Buffalo. NASA researchers have shown that cities ringed by forests, which cool more than agricultural areas, tend to have a greater temperature gradient between city and rural fringe, and hence a more pronounced heat island effect, as seen here. I would ask that you look over the conclusions and basic understandings at the end of the chapter to give you some idea of the highlights of the PowerPoints and the chapter's important information.